Friends, welcome to the second lecture on module 3, where we are focusing on risk assessment and reliability applications. In this lecture, which is the second lecture in module 3, we will talk about design SN curves. In the last lecture, we discussed about the fatigue assessment in terms of using SN curves. We have also seen what are the limitations with respect to the SN curve data as specifically applicable to offshore structures. Extending the same discussion now further, we already said one is interested in knowing the cumulative damage. We also said, as per the minus rule, failure under variable amplitude loads which is a general case in offshore structures, is true when the following condition is satisfied. The condition is summation of, let us say, G to the entire group dG amounts to unity, which is a general failure function which is indicating a cumulative damage of all the elements in a given system. This is what we refer to as essentially fatigue spectrum. The Palmgren-Manner rule actually ignores one important aspect which can be considered as a negative issue. The Palmgren-Manner rule ignores the load sequence effects. Which may be very important in case of identifying the system reliability of offshore structures. So, what in general we want to say here is the conventional conservative SN approach may also land up in estimating very wrong stress concentration factors based on which a system reliability can be computed for fatigue failure. Further, when the study or discussion apply to offshore structures, the mean stress effects are generally not considered. So, we are talking about the stress range, but the mean stress effects are not considered in the model of conventional SN approach. This is what is critically stated by Gong et al. In 2007. Therefore, there are some limitations in the study of fatigue assessment in offshore structures. So, one can say here limitations exist in fatigue assessment of offshore structures under the combined effect of one, material degradation and stress cycles. So, accounting for all these deficiencies or limitations in the fatigue assessment, generally people say that a cumulative damage, what the equation said, as sum of G equals summing from G, which is going to be dG equals 1, is modified to 0.5. On the other hand, even if the sum is closer to about 50%, it is considered to be a damage scenario, because the combinations are very extreme, because the material degradation is directly linked to the stress cycles, and we are not considering the mean stress cycle or mean stress effects in the given system. And most importantly, the whole approach do not consider the load sequence effects. So, considering or adding all these consequential effects in the overall estimate of cumulative damage of failure assessment, instead of rounding off this to 1, people have modified this to 0.5. Interestingly, there are other factors which can also affect the damage assessment. For example, the techniques used for dressing, TIG dressing we call, can also improve the fatigue strength. Over a gas welded specimens. In particular, that is one issue. As we understand, offshore structures are essentially elements comprising tubular joints. Therefore, there are some specific factors which should be considered in fatigue assessments of tubular joints. One could be the standard definition of fatigue failure of tubular joints employed in the test. One has got to actually define what do you mean by a failure of a tubular joint, especially during test conditions, because tubular joints essentially fail in many different ways, which we will explain you later as a case study. You will understand that the stress concentration factors and the load carrying capacity estimates made from the conventional equations vary significantly with that of the actual load carrying capacity of a tubular joint under failed conditions under the experimental investigations. We will show you later. So, it is very important to define the standard failure of a tubular joint under test conditions. Secondly, size of the tubular joints. Size of the tubular joints play a very important role, and that should be pre-decided. As the size has a very significant effect on the fatigue strength. Since it has a significant effect on fatigue strength. For example, tests show that larger joints have lower fatigue strength. Third factor could be shape of the toe weld. Which is also important in estimating the fatigue behavior of welded joints. Fourth could be the post weld treatment. This can significantly affect the results of a fatigue assessment and should be stated prior to the test. There are other different variables which can also involve or which can influence the fatigue assessment of tubular joints. The other factors could be seawater corrosion or the corrosion caused by seawater, stress ratio, that is max to min. What is the range you are talking about? Type of loading. Fourth, sequence of loading. You can say sequence of loading, unloading, especially during erection, commissioning and placement. Then weld improvement techniques, since there are no equations or no parameters which can significantly include these factors effect on the fatigue assessment as well as the parameters which are majorly influencing the fatigue assessment, like definition of failure, size of the tubular joint, weld treatment, shape of the weld, etc. One should account for all of them indirectly. So, the fatigue assessment of tubular joints should account for the above factors which a conventional SN approach cannot. So, therefore, we go for design SN curves. Various classification societies have recommended design SN curves for both kinds of structures. Design SN curves are recommended by classification societies for both plate type and tubular joints. For example, American Bureau of Shipping, American Welding Society, American Petroleum Institute, etc. Many societies there are many classification societies which describes the design curve. Two typical recommendations will be discussed here. Okay. Let us talk about one recommendation given by APRP 2A. talk about APRP typical recommendation made by APRP 2A. It says that following form of SN curve can be used, that is n equals 2 10 power 6 delta sigma by delta sigma reference raised to the power minus m. The modified SN approach could be including the thickness of the plate with reference to the reference thickness minus 0.25 m. That is one typical recommendation given by the classifying society APRP 2A. The other one could be the Norwegian standards. Which is NS 3472 E. It recommends the following form. Let us say in air, for the number of cycles less than 10 power 7, it says 12.16 log T by 32 minus 3.0 log delta sigma, equation number 3, where T is in millimeters is the thickness. In water, for n less than 10 power 8, log n is 12.16 minus 0.75 log T by 32 minus 3.0 log delta c. That is for 10 power 8 cycles, whereas in air 10 power 7 cycles. I think this equation (12.16) minus 0.75 log T by 32. So, for 10 power 7, there are 10 power 8 cycles in water. So, equation number 4. One can easily see that the above design SN curves as recommended by the classification societies cannot be applied until a suitable stress concentration factor is known. Now, to apply this, one has got to use parametric equations. So, to obtain the stress concentration factors, one need to use parametric equations. Now, these parametric equations are developed these parametric equations are generally developed for typical joint configurations using experimental and numerical modeling using finite element method. But interestingly, what we are bothered about is between these two they show a lot of discrepancies. So, friends, even at this point of time, though design SN curves are recommended by various classification societies to be used for offshore structural design, there has been quite significant discrepancies which are indicated, which are implicitly present when you derive these equations for the stress concentration factor, essentially based by two different techniques, one is experimental, another could be numerical. So, one is interested to know what is the probability of failure when the system is subject to cyclic loads, what we call fatigue assessment or fatigue failure. Even assessing the fatigue failure itself, there are inbuilt implicit uncertainties which are even available even at the design stage, which is supposed to account for lot of other uncertainties present in the design SN curve, which is supposed to be an improved form of a conventional conservative SN approach, which is suggested by various researchers. So, now let us see one such approach which talks about fatigue assessment, which we call discrete wave approach. Now, to enable faster fatigue calculation using discrete wave approach, people have suggested two versions of SH relationship, where S stands for the stress concentration or the stress range and H stands for the wave height. So, these are nothing but one could be a quadratic model to estimate the SH relationship, the other could be a power form. Both are discussed and available at Marshall 1974, (1976) A and B. Let us quickly see what do we understand by SH relationship, which is used for fatigue assessment. The most time consuming part, dear friends, in doing a fatigue assessment is to actually establish a simple relationship between the stress range at any point of interest on the structure and the wave height. So, S stands for the stress range at any point of interest in the structure, and H stands for, let us say, wave amplitude, essentially wave height. Let us now see the quadratic form of this relationship. The quadratic form of the relationship is given by S equals A1H plus A2H square, where the constants AI can be obtained by the least square fit to stress values. Which corresponds to simple wave loading. This is very important. Now, there are few facts which are very important to note in a quadratic form. 1. Please note that there exists a linear contribution which is valid only when A2 is much less than A1. B. Instead of simple wave loading, one can also use higher order wave theory. So, one can retain the nonlinear terms in Morrison equation, and they can be used to estimate the HH relationship. So, now using the quadratic form, Sn relation can be now modified. One can say n is now equal to A1 to the power minus m, because I am rewriting the same in form of Sn relationship is going to be 1 plus A2H by A1, normalizing it to the power minus m, equation 5. Alternatively, one can also use the following SH relationship instead of a quadratic model. One can use a power form where S is expressed as C h to the power g, where the constant C and G are obtained by least square fit to stress cycles. to stress values corresponding to simple wave loading, it can be even any sample wave loading. In such case, the SN relationship can be rewritten as n is equal to A C minus m H minus mg, which I call as equation number 7. We know now, according to Palmgren-Minor rule, the cumulative damage is given by damage index D with sum of NSI by capital NSI, equation number 8, where small n denotes the number of cycles experienced at stress range, number of cycles experienced at the chosen stress range, and capital N denotes the cycles to failure. So, the stress range is SI, and D is the total damage. In fact, this is nothing but called also as damage ratio, looking for the ratio actually, okay, damage ratio accumulated due to all stress cycles experienced by the structure. Now, interestingly, a member or a connection is assumed to have undergone failure if D is equal to 1. D is equal to 1 as per the minus hypothesis. Somewhere we also said, accounting for various other uncertainties, this is also reduced to 0.5. Okay. Now, the fractional damage caused by the wave cycles can be written as the fractional damage is dd, which is dn by n, which implies that the connection has undergone dn cycles the connection or the member has undergone dn cycles of a stress range for which the failure occurs at n cycles. So, this n cycle failure is pertaining to SN data which is prepared based on some experimental investigations. One is now interested to know the fatigue damage. Using the above relationship and assuming that using the above equations and assuming that A2H by A1 is much lesser than 1 and neglecting the higher powers. Integrating the equation between the limits 0 to infinity, one can obtain the damage. One can obtain the damage as, so we are equating the SN equation between the limit 0 to infinity, neglecting the higher order powers and assuming that this condition is satisfied for a SH approach model using a discrete way. We can say D is given by M A1 delta to the power M by A gamma function of 1 plus M by nu plus A2 delta M A1 gamma function of 1 plus M by nu plus 1 by nu. Equation number 10. Let us say the gamma function of any variable p is actually a gamma function and defined as gamma of, let us say, p is integral 0 to infinity t to the power of p minus 1 e to the power of minus t dt for p greater than 0, equation number 11, where in equation 10 m is the total number of waves in the C state under consideration. Let us now consider a 2 segment SN curve damage is given by let us say D is equal to M A1 delta by A to the power m gamma function of 1 plus m by nu z plus A2 delta m by A1 gamma function of 1 plus m by nu plus 1 by nu comma z plus m A1 delta by C is to the power r gamma 0 1 plus r by nu z. Okay, here I close this gamma function plus A2 delta r by A1 gamma function of 1 plus r by nu plus 1 by nu z. Equation number 12. So, the gamma function of p comma z is given by integration z to infinity, not from 0 to infinity, t to the power of p minus 1 e to the power of minus t dt is also equal to gamma of p minus gamma naught of p z if p greater than 0. Equation 13. In the above equation, please note that gamma 0 of A z similarly gamma A are actually called incomplete gamma functions. Where z can be simply said as SQ by delta. So, one is also interested in long term fatigue damage. Now, one is interested in long term fatigue damage. So, long term fatigue damage due to C state can be modeled as an exponential distribution obtained by setting the limits in the equation and denoting the parameters in terms of slope of the Hn plot. So, for the given SH relationship, let us say in the power form, because there are two forms by which you can explain this. One is a quadratic form, other is a power form. The damage expression equation for two segment SN curve is given by D equals m delta Gm C to the power of m by A gamma function of 1 plus Gm by nu z plus m delta Gr Cr by A gamma function of 1 plus Gr by nu z. Equation number 4. So, friends, one can also find the design SN curves which has got lot of discrepancies between that of the experimental and the numerical finite element method suggested by the classification societies. One can also use discrete wave approach as we have been discussing so far. In two forms one can express the wave. One can also take the nonlinear terms in the wave loading and preserve them in the Morrison equation, and one can find the damage estimates. So, we have discussed a two segment curve appropriately modified for a given SH approach, what we discussed so far in this lecture. We will discuss further a simplified fatigue assessment method, because this method seems to be a roundabout complication which is very detailed. This can also be substituted by a simplified assessment for fatigue damages, which we will discuss in the next lecture. Thank you very much.